Alright, so in today's video we're going to be talking about logistic regression and what that is. So in the previous video we talked about linear regression, and linear regression is very good for predicting continuous values. But logistic regression is more attuned to classification and predicting discrete values. So what do I mean by that? Well, a discrete value would be something like we see here. There's a set of values and you can only be one or the other. So here we have three possible options here, and you can't be like in between any of these little nodes. And these nodes could represent anything, such as vehicles that you might be classifying in an image. You can't be like half a truck, half a car. It doesn't work. You have to be one or the other. But over here we have continuous values, and if we're predicting, say, the price of a house, that could be anywhere on this scale. Of course, this is a little bit of a small scale for house prices, but you get the idea. It can be anywhere between these values, while discrete values, only a few specific values you can occupy. So typically, we divide these up into classes. We want to predict which class something is a part of. And that's what we use logistic regression for. So the way we do this is that we want to utilize the same sort of h of x function that we use for linear regression, but the problem with that is that if you use that, it's very susceptible to outliers whenever you're doing classification, and you can also potentially end up with an interesting situation where you predict a less than 0 or more than 100% probability for something, which obviously doesn't make a whole lot of sense. So to combat this, we use this function here called the sigmoid function, and this is what it looks like. And as you can see, it has horizontal asymptotes at 0 and at 1. So this represents our probability. It's something between 0 and 1. And it sort of intercepts the y-axis right here at 0.5, as you can see. So the negative x in this case represents our x-axis down here. And we want the negative x to essentially be where we plug in our previous h of x function. So for negative examples that are not positive, we want to push that towards a negative value so we get a close to 0% probability. While for positive examples, so when you have a class that's a 1, we want to push it to a larger value so that we get a high probability of it being the case that this is a positive example that we're seeing. And positive and negative example is basically the terminology we use when we're talking about binary classification. Something either is or it is not. It is positive or it is negative. And so if you had, say, a cancer diagnosis machine here, you could say that a malignant tumor would be the positive case because that's the presence of a tumor, while the benign tumor would be the negative case because that is the absence of cancer. So typically, the positive case is the presence of something, and the negative case is the absence of something. So this would be benign, and this would be malignant. So you would see something close to 1 if you were very confident in that assertion. And so that's the basic idea of logistic regression. It outputs some probability of a binary classification. So what's our cost function here? Well, our cost function is actually two functions in one. So if our example is positive, we say that our cost function is negative log h of x. But if it is negative, we say it's negative log 1 minus h of x. And the reason we do this is I plotted these two curves right here. So this first curve would be if the example is positive. So if you predict that you get a 1 out of the sigmoid function, you have a very positive number plugged in and you get something close to 1, your cost is very low. But as you get more confident that it's actually a 0, the cost is high. Because we have to understand is when you look at the sigmoid function, 0.5 is typically the cutoff. Anything less than 0.5 we say is negative. Anything more than 0.5 we say is positive. And the farther away you get from the center, the more certain, the more confident you are in your classification. So if we have something that's like negative 2,000 over here, we say that it's very, very confident that this is a negative case. So if you give a very large, you give a very small output from your sigmoid function, you had some extremely confident result that it was negative when it was actually positive, you get a very large loss function. A very large cost is accumulated. While in the inverse here, if it's a negative case and you say it's negative with high confidence, then you get very little cost. And inversely, if you say with high confidence that it is a positive case, you get a large cost. That's the general idea of using this two-cost function system. So it's a little bit different than the mean squared error that you see in linear regression, but this is actually a very effective way of calculating cost. So what's your h of x? Well, this is just the linear regression thing we talked about earlier. So the weights that your model is actually adjusting are in this h of x, which we plug in here. That's where the weights are that are being adjusted. So we want negative cases to have very negative values. We want positive cases to have very large values. That's the idea. But you might be thinking, okay, well, this is all good and all. But what if I don't want to do binary classification? What if I want to do multi-class classification? Well, the technique that we generally use is called one versus all classification. And here, if you have k classes, you create k sigmoid functions with k outputs. And you make sure that all of your outputs sum to 1. Okay, so what am I talking about here? So let's say you wanted to classify between 5 different fruits. You had an image classification. You would have 5 different sigmoid functions, and each sigmoid function would be responsible for classifying the probability that the image is of a specific type of fruit. So you could have one that classifies whether it's an apple or anything else. You have another that classifies whether it's a banana or anything else, and so on. This is called one versus all, because each classifier is calculating the probability that it is one specific class or that it is any of the other classes. That's what each individual probability represents, and of course they all have to sum to 1. And this changes the cost function a little bit. So instead of getting, the typical cost function where you're just taking the two-function system, here we're sort of getting like an average of them. But it also has an interesting effect on actually implementing it, because typically with binary classification, you can represent your y vector, your outputs, as just a 1 or 0, and that's very easy to store on the computer. But if you have a large classification algorithm using one versus all, what you need to do, because the outputs are being outputted as a vector, as several different probabilities, you need to make sure your y outputs represent that. And so you need to make your y's a multidimensional vector. So here, let's say, we're basically saying this probability should be 0, this probability should be 1, and this probability should be 0. So that makes it take up a little bit more space on the memory of the computer, but it's worth it in the end. Okay, but what if I'm dealing with skewed data? What if I'm dealing with data such that, in the cancer example, only 1% of our examples are actually a positive case? Well, using accuracy as the metric here actually doesn't really work. And the reason for that is because you could create a model that predicts no one has cancer and get 99% accuracy. So accuracy becomes a very crude metric when you have skewed data. That's not very effective, okay? So what you want to do instead is use precision and recall. And what we're talking about here is, let's say we assembled this table here. So here up top we have the actual classification, and here we have our predicted classification from our algorithm. So if both are positive, we call this a true positive. That's when you correctly classified the positive case. If you classified it as positive but it was actually negative, we call this a false positive. And then we have true negatives when it's actually negative, and that's what you classify, and false negatives when you classify it as false but is actually true. And so precision is we're basically asking, it's true positives divided by all of our positives. We're asking, of everything we classified as positive, how many were actually positive? What percentage of them were really positive? Here, our recall is our true positives divided by true positives plus false negatives. We're basically asking, of everything that was actually positive, how many did we catch? How many did we classify correctly? And these two metrics are much more accurate than just accuracy, which can become quite crude. So typically, when we want to increase one, it comes at the cost of the other. So if we want to increase recall, we might see a decrease in precision. And the trade-off there really just depends on the context of what you're doing. So for cancer, you might want a very high recall. You might want to make sure you actually get all the cancer cases, but there are other instances where precision would be more valuable. So that was just a very brief and general rundown of logistic regression. And we'll see you guys